So maybe change something, I don't know, and then she checked that, sorry that I don't know the name. She went outside to make sure that people at room can hear, but I guess they changed the microphone, some mic here. Okay, she said that. I know this, I'll meet the person at the audience. Okay, cool. I'll check that. There should be, maybe it has been online, maybe because I have downloaded. Thank you so much. Yes.
Okay, let's go ahead and get started. Welcome to our CX Colloquium. My name is Aaron Calzette. For those of you who don't know me, I'm a professor here at the Department of Computer Science. And it's my great pleasure today to introduce our speaker, Dr. Ramin Ayanzadeh. He's a Computing Innovation Fellow at Georgia Tech. He holds a PhD in Computer Science from the University of Maryland, where he worked with Tim Finnan and Milton Hallam. His research agenda aims to construct an abstraction layer that connects quantum architecture with quantum algorithms, providing more robust, more versatile, and more trustworthy quantum computing services to problems as varied as security, machine learning, and optimization. For his talk, in the interest of time, let's hold substantive questions until the end if you have them, but if you have clarifying questions, feel free to ask them during the talk. So please join me in welcoming Dr. Ayanzadeh.
Thank you, Aaron, for the kind introduction. I'm truly honored for the opportunity to be here today. Today, I will be discussing how we can develop software policies to improve the reliability and security of quantum computers. But before I begin, I would like to go over some logistics. As a speaker who is blind, I wouldn't see if you raise your hand to ask a question. So anytime you had any comment or question, please feel free to speak up. Let's get started. When we look at supercomputers, we see a huge speed up over time. These days, conversations are around exascale computing. I have no doubt that we will be able to deliver greater speed up soon. But our main challenge here is not to provide more speed up. It is about problems that will remain intractable even if we can provide orders of magnitude speed up. So simply waiting for the next generation of supercomputers is not enough. For example, if we want to factor a 2000-bit number using the largest supercomputer we have, it would require the energy of Earth and over 100 years to perform the computation. On the other hand, a quantum computer can handle this task in just about 8 hours. Quantum computers have potential to tackle many important problems that are beyond the capabilities of classical supercomputers. These important applications appear in various domains such as optimization, drug discovery, cryptography, but I should highlight that for problems that classical computers can handle, we will keep using them. In other words, quantum computers are domain-specific accelerators, and we need them specifically for those applications that classical computers cannot and will not be able to handle. I would like to also highlight that the applications of quantum science and technology goes beyond building computers. In fact, we can leverage quantum to take navigation systems, clocks, and sensors to the next level. But let's focus on computing and see what is a quantum computer. In classical computing, we have a bit, and the state of a bit can be either 0 or 1. We all know that. In quantum computing, we have quantum bit or qubit, and the state of a qubit can also be 0 and 1. We use this notation to distinguish between the classical and quantum states. But in addition to 0 and 1, the state of a qubit can be any point on this sphere, which means that a qubit can be in superposition or a linear combination of both 0 and 1. And here, alpha and beta are complex amplitude defining the amount of being 0 and 1. But regardless of where the state of qubit is, anytime we measure the state of a qubit, it collapses to either 0 or 1 with their corresponding probabilities. We need the ability of manipulating the state of qubits to perform any meaningful computation. Here, rotations along x, y, and z axis are enough for any arbitrary single qubit operations. But there are a few specific rotations that appear in most quantum algorithms. So we use simple letters or notations for streamlining our explanation. For example, if we apply pi rotation along x-axis, we simply call it x-gate. X-gate is analogous to NOT gate in classical computing, and it flips the amount of being 0 and 1. In the same way, we can have y and z gates when we apply pi rotation along y and z axis, respectively. Another very common single qubit operations that appear in most quantum algorithms is called Hadamard, which applies a pi rotation along x-axis, followed by a pi half rotation along y-axis. And in fact, if we are in north or south poles, Hadamard brings it to the equator, where both 0 and 1 have equal probability of observation. These single qubit operations are enough for any arbitrary state manipulation. However, we are not ready yet to outperform classical computing. To outperform classical computing, we need a form of cooperation between qubits, which is called entanglement. And we use multi-qubit gates to make this entanglement. Conditional NOT or CNOT is the most commonly used multi-qubit gate that appears in almost all quantum algorithms. It involves 2 qubits. If the state of the control qubit is 1, we apply X gate to the target qubit. Otherwise, we do nothing. Now, we are ready to build a universal quantum computer that can outperform the largest supercomputer we have. In quantum computing, we use quantum circuits for visualizing the quantum information processing. Here, we see a simple yet important circuit, including 3 qubits, that always produces all zeros and all ones with equal probability. Roughly speaking, just about 60 qubits are enough for demonstrating the supremacy of quantum computers. Quantum companies, major players such as IBM, Inflection, and Atom Computing, last 2 are in Colorado, have recently unveiled their quantum processors with more than 1,000 qubits. So the question here is, if we need just 60 qubits, and we only have quantum processors with more than 1,000 qubits, why can't we demonstrate quantum supremacy now? The issue is that quantum hardware is noisy and prone to several error sources that prevent us from reliably running quantum programs. For example, quantum bits experience decoherence, which means that they can hold quantum information for a very short period of time. State preparation and measurement are also inaccurate. Additionally, quantum operations are inaccurate. And since any point on the sphere is a valid state, we cannot distinguish faulty operations. Moreover, quantum computers are vulnerable to unwanted interqubit interactions, which is called crosstalk. For example, here, our goal is to apply a CNOT between qubit 1 and 2. But the state of the adjacent qubit 3 can be also manipulated. In quantum, we have 2 approaches for handling the noise. In the fault-tolerant regime, we use quantum error correction to protect both quantum information and quantum operations. In QAC, we form a logical qubit where the state of a reliable qubit is distributed over several physical qubits. We also use several parity qubits to detect the type and location of errors on physical qubits. QC is promising, but accommodating its overhead in near term seems to be impractical. One logical qubit may require hundreds or thousands of physical qubits. Even if we can provide such a large number of physical qubits, performing logical operations on these logical qubits is non-trivial. Additionally, the entire process of detecting and correcting errors needs to be done in real time. For example, in superconducting case, it has to be done in less than 1 microsecond. In our recent work, PROMAC, we were able to enhanced the state-of-the-art for real-time decoding of surface code for up to distance 13. Previously, it was 9, and we are going to present it in about 2 weeks at ASCMS. On the other hand, we have NISQ regime, where we don't try to detect and correct errors. Our goal here is to perform computations at the presence of nodes. To solve the problem, we design a quantum circuit, compile it to make the executable, and run it on the quantum hardware. Running this circuit should always produce all zeros and all ones, but since the quantum hardware is noisy, it might produce 001, which is erroneous. But if we repeat the computation many times, instead of having one single outcome, which can be erroneous, we might get a distribution of outcomes. And our goal in NISQ regime is to post-process this output distribution to infer the desired solutions. In fact, NISQ regime is promising, and we can tackle certain problems much better than classical computing in domains such as optimization, machine learning, and quantum simulations. Here, our focus will be on optimization. In classical computing, we have a computing stack that transforms the input program into instructions that underlying computer can execute. The system and architecture layers are responsible for efficiently performing these transformations layer by layer. Analogously, we have a quantum computing stack, which transforms the input quantum algorithm into pulses that the underlying quantum hardware can execute. But in quantum, as we discussed, there's a huge gap between the expectations of the quantum algorithms layer and the reality of quantum hardware. System and architecture of quantum computers is an emerging field where we try to bridge this gap. Actually, my primary area of study is the system and architecture of quantum computers, and my goal is to develop policies across different layers of the quantum computing stack, ranging from application layer, programming languages, and compilers, all the way down to error correction, to improve the reliability, security, and enhance the broader applicability of quantum computers. Quantum computers come in many different flavors. For example, qubits can be developed using different technologies. I have experience with superconducting, and I've recently started working with neutral atoms and trapped ions. Additionally, quantum computers can be digital and analog, and I've experience with both types. Moreover, quantum computers can be categorized in different computing models. I have background with adiabatic and gate-based models, and I'm going to start working with measurement-based or one-way quantum computers. And I should highlight that all these various types of quantum computers can be employed in both fault-tolerant and NISQ regime. But in today's talk, I'm going to discuss two of our recent work, first focusing on how we can improve the reliability, and then how we can protect the security of near-term quantum computers. QAOA is a leading candidate for demonstrating the supremacy of quantum computers in near-term application. The goal in QAOA is to approximate the global minimum of this NP-hard optimization function. Let's take max cut as an example. To solve a max cut using QAOA, we need to first design a quantum circuit. QAOA circuits are multi-layer, and in each layer, these layers are repeated. They are all identical. Every edge of the problem graph, as you can see, is represented with two CNOT, conditional knot that we just discussed, along with one rotation, RZ rotation. And at the end, all qubits receive rotations along x-axis. The point here is that the values of these rotations are not fixed. In fact, an order loop classical optimizer tunes these parameters towards converging to the global minimum. The key takeaway here is that every edge of the problem is represented with two CNOTs in each layer. Now, let's take a closer look and see how many CNOTs are involved in practice. Well, the problem graph needs to include at least 500 nodes. Otherwise, it can be tractable by classical computers. We also need to repeat the circuit at least 12 or 13 times to provide enough accuracy. So depending on the topology of the input problem graph, we will need to run circuits with thousands or even millions of CNOTs. These numbers are magnified when we compile quantum circuits. Here, we see the connectivity map of IBM Montreal, which we use for evaluating our experiments. As we can see, qubits are sparsely connected. To apply a CNOT between two qubits, we must first make those two qubits physically adjacent. We can use swap operations and route qubits, but swap is costly as each swap is decomposed into 3 CNOTs. This chart shows the number of CNOTs before and after compiling. As we can see, the number of CNOTs before compiling increases linearly, but post-compiling, it increases super polynomially. The issue here is that these CNOTs are very noisy. On average, every CNOT has an error rate of about 2% on current systems. So we can reliably run circuits with about 60, 80, 100 CNOTs. But we need to run circuits with millions or even billions of CNOTs. And the key takeaway here is that the difficulty of optimization problems in classical computing can primarily depend on the number of nodes. But in quantum, the hardness of an optimization problem can depend on the number of edges. But not all qubits are the same. Here, we see the connectivity map of connections in US airports. As we can see, there are a few hubs or hotspots that have more than 10x degree compared to average degree node in US airport connection. And this is not limited to airport connectivity. Actually, we have learned that in most real-world problems, today I learned that I shouldn't use the term power law. Most real-world graphs have a long tail, which means that there are a few hubs or hotspot nodes with a very high degree. So if we can find a way to skip these hubs or hotspots, we can significantly improve the reliability of quantum circuits. But unfortunately, current circuit cutting techniques are not able to deliver this because partitioning circuits with edge cutting or cutting wires when we have high degree nodes seems to be infeasible. And to that end, we introduced FrozenQubits, and I presented it last year at ASCLS. The idea behind FrozenQubits is simple. Let's say we want to eliminate one hub or hotspot. We duplicate the problem graph. We have two copies identical. Since after the measurement, the value of the qubit, every qubit will be either +1 or -1, in the first copy, we substitute the variable represented that node with +1 and in the other one with -1. And removing that variable removes all edges connected to that node. Now we have two subgraphs, each representing to the half of the search space. And we run quantum programs associated with these two subgraphs to guarantee that we are not missing any point in the search space. And we can continue this process. To evaluate the impact of FrozenQubits, we use Barabasi-Albert algorithm for generating random power law graphs. And we use approximation ratio gap for measuring the quality of solutions. This arc measures the results compared to running on an ideal situation where the quantum has no noise and lower is preferred. This chart shows the arc of standard QAOA compared to FrozenQubits when we only skip one or two hubs or hotspots. As we can see, the standard QAOA, the baseline, it diverges quickly, and after some points, results become random numbers. But in FrozenQubits, the rate which arc is diverged is much slower. And in fact, we observed that by removing up to 2 nodes, the fidelity of quantum programs on IBM devices is increased up to 57 times. Well, why this huge improvement happens? The reason is that on the top chart, we see the number of CNOTs, and in the bottom chart, we see the depths of the circuits when problem sizes increase and we eliminate 1 or 2 hubs or hotspots. As we can see, the number of CNOTs at this depths of the circuits in FrozenQubits grows significantly in a lower pace. Now, CNOTs directly correspond to the noise, and depths of the circuit corresponds to the decoherence, and that's why FrozenQubits delivered such a huge improvement. FrozenQubits is a software policy that improves the reliability of QAOA without manipulating the underlying hardware. But reliability is not the only concern in quantum computing. Next, I'm going to switch to another important aspect of quantum computers. The typical model for performing quantum computation is to submit the quantum program to a quantum cloud provider. This raises significant concerns, specifically because problems that we are going to solve on quantum computers are those that classical supercomputers cannot handle. And for commercial entities, this can raise lots of concerns. Secure quantum computing is an emerging field where our goal is to protect the security and privacy of quantum users. It can be classified into two main groups. In blind quantum computing, we partially delegate the quantum operation or circuit to the server. To enable this, we need the client to also have a small quantum computer, and we need a quantum network connecting these two quantum computers. But quantum networks is an emerging technology which does not exist yet. It's under development. Quantum homomorphic encryption enables us to perform computation in encrypted manner, but it introduces exponential computing overhead. And without quantum error correction, it's impractical. Unfortunately, current SQC techniques are impractical for near-term and existing quantum computers. The reason behind impracticality of these techniques is their objective to be generic and applicable to any quantum circuit. To address this, we introduced Enigma, where we propose the idea of application-specific secure quantum computing. The idea here is that instead of applying obfuscations to the circuits or executables, we bring the obfuscations to the application layer and we encrypt the problem. This enables us to develop SQC techniques that are readily deployable on existing and near-term quantum computers. But now the question is, which application? Well, we again come back to QAOA for two reasons. A, as we discussed, QAOA is among the leading candidates for demonstrating quantum supremacy. So protecting its security must be more important than other applications. And B, as we discussed, the way we create quantum circuits here has a pattern. And this pattern enables the attacker to quickly retrieve the original problem that the user wants to solve. And I should highlight that here, intellectual properties are the problem, not the algorithm. In this study, we focused on passive attacks, where we assume that untrusted server may misuse our information, but it does not tamper with the outputs. QAOA problems include three types of assets: nodes or variables, edges, and edge weights. And we introduced three variants of Enigma to safeguard these assets. Next, I'm going to introduce Enigma 1, which manipulates the coefficients of a problem in a way that both the input and output becomes inaccessible to the server. In QAOA, we use spin variables, which means they take their values from -1 and +1. So if we apply a spin variable by -1, this action will act like a spin flip. Enigma 1 leverages this property to manipulate coefficients. We start with randomly selecting a subset of qubits. This list, which is represented by T here, serves as the encryption key. After selecting the encryption key, we toggle the sign-off coefficients connected to them. Let's take a closer look and see how it works. Here, we have top 8 outcomes for a problem and its obfuscated version. If we compare the global minimum of these two functions, we'll see that those qubits that have been selected, Z2 and Z3 here, their values in the ground state of the obfuscated problem has been flipped. And since the server does not have access to the encryption key, from a server perspective, it will act like random flips on the output. So far, we have applied random spin flips on the output. We have manipulated the sign of the coefficients. Now our goal is to hide the magnitude of coefficients. Here, we multiply all coefficients of the problem on the left side by 1.3 and 0.7 and represent it. As we can see, when we multiply all coefficients of an optimization problem by a positive number, we are not changing the order of states. So we are not going to change the position of the global minimum, but we are going to only reduce or increase their distance. So as a last step, we generate a random positive number and multiply all coefficients by that number. Here, we see the overview of Enigma 1. We start with randomly selecting a subset of qubits to form the encryption key, which is not shared with anyone, encrypt the problems, and then create the circuit for the encrypted problem and send it to the server. Since the server is solving a different problem, the outcomes need to be deciphered. Here, the coding is straightforward, as the client just needs to apply spin flips for those qubits that are in the encryption key. Now, the question is, can this process impact the quality of solution? Here, we are solving a different problem. We manipulate the problem, and it can have a different global minimum. So we need a mechanism to measure the quality of solution. So we introduced a new metric called restricted approximation ratio, which computes the expected value on top k most frequent outcomes divided by the global minimum. And here we set k to be 5. This chart shows the mean RAC relative to the baseline across different benchmark problems. And we observed that Enigma 1 deviates from the baseline by an average of only 0.7%, which is negligible compared to the errors and noises in quantum computers. The reason behind this similarity is that both baseline and Enigma 1 can share the same circuits, as all changes happen in the rotation values. By manipulating the coefficients of the problem, Enigma 1 enables us to hide the coefficients and also apply spin flips on the output. But still, there are some information that are accessible to the server. For example, the attacker knows the exact number of nodes, and it has access to the exact structure of the problem. To address this, we introduce Enigma 2 that adds decoy or fake nodes to the problem and makes perturbations to the structure of the problem. Enigma 2 starts with bringing the problem or mapping the problem from Ising to QAOA, where we work with binary variables. Binary variables means they take their values from 0 and 1. But why do we this switch? There should be a reason for that. The reason is that we can represent the objective function as a matrix product. Here, X transpose AX, where X is the binary vector representing variables, and A is the coefficient matrix. And Enigma 2 leverages this matrix representation to introduce decoy or fake qubits. But what does it mean to introduce decoy qubits? From a graph perspective, it means that we introduce new nodes and add new edges to the problem graph. From a linear algebra perspective, it means that we append some new binary variables, here denoted by y, to the end of the primary vector, and we extend the coefficient matrix. To expand the coefficient matrix, we define two smaller coefficient matrices, here B and C, and attach them to the original coefficient matrix. Now the question is, how we define these values, the matrices B and C? Because remember that our goal here in QAOA is to solve an optimization problem. Protecting the security and privacy is essential, but if we cannot solve the problem, our effort will be useless. In other words, the client needs to be guaranteed that he or she will be able to retrieve the global minimum of the original problem using the global minimum of the obfuscated problem. Mathematically, this is a very challenging task. To make it tractable, we made two assumptions. First, we assume that the primary qubits take same values in global minimum of both primary and obfuscated problem. Second, we assume that all fake nodes take 0 in the global minimum of the obfuscated problem. This resulted in a much simpler problem, which says matrices B and C needs to be only non-negative. How we came up with this? It's a little bit math involved, and if you are interested, you can reach the paper, which is on archive available. But we are not secure yet. If we append all variables to the end of the binary vector, the attacker can identify most, if not all of them. To address this, we shuffle the order of primary and fake qubits. To this end, we generate a permutation matrix, which is an identity matrix shuffled column-wise, and then multiply the augmented coefficient matrix by this permutation matrix. After receiving the outcomes, the client simply needs to multiply the outcomes by the transpose of the permutation matrix to bring the bit string back to the original order. Here we can see the overview of how Enigma 2 works. We bring the problem to the binary domain, introduce new nodes, new edges, and then shuffle the order of qubits or permute them. But we need to bring the problem back into Ising domain because that's where we know how to create quantum circuits. And since we are in Ising domain, since we are back to Ising Hamiltonian, we can optionally apply Enigma 1 as the last stage for encrypting and hiding the coefficients as well. I should highlight that for decryption, the client needs to perform decryption in reverse order. So first, it applies the decryption of Enigma 1, then the permutation is undone, and lastly, the decoy values are dropped. This chart shows the mean RAR of Enigma 2 relative to baseline across different benchmarks. And we observed that the Enigma 2 deviates from baseline by an average of 2%. Recall that when we introduce decoy nodes, we also need to connect them to the primary node. And adding new edges introduces new nodes. But I should highlight that we do not need to increase the number of fake nodes when problem sizes increase, because the attacker does not know how many decoy qubits we are adding. This chart shows the relative impact of Enigma 2 when we increase the problem size, but the number of decoy qubits keeps the same. And we can see that when problem sizes increase, the relative impact of adding or introducing decoy qubits is diminishing. Enigma 2 enables us to protect most aspects of QAOA, but still there are some residual risks. For example, in graphs with hubs or hotspots, simply adding a few nodes cannot hide the identity of these hubs. And if it is important, then we are failed. To fully protect the security of quantum computers in QAOA, we introduced Enigma 3, which ensures that the output graphs also becomes regular. In 1961, Paul Erdos, the famous mathematician, asked a question, which was, can we make any arbitrary graph regular by adding new nodes and new edges? And then he provided necessary and sufficient conditions to solve the problem. This is exactly what we want. And after more than 6 decades, we were able to find an application for the problem that he had introduced before. And our contribution here was to effectively finding the minimum number of these decoy qubits to make the problem graph regular. We first started with satisfiably modulo solvers, but then realized that they are not efficient. For problems with few tens or hundreds of nodes, it was taking many hours. So it was not practical. We demonstrated that the number of decoy qubits cannot exceed the number of primary qubits, and then a simple linear search from 0 to n enabled us to find the minimum number of decoy qubits required to make the problem graph regular. The key distinction between Enigma 2 and 3 is that in Enigma 2, users defines the number of decoy qubits, but in Enigma 3, the problem topology dictates the number of required, the number of decoy qubits required for making the problem regular. This chart shows the relative number of 2-qubit gates and depths of the circuit when we increase the problem size. As we can see, these factors, circuit factors, increases linearly with problem size increasing. This chart shows the mean RAR relative to the baseline across all benchmark problems that we had. We observed that Enigma 3 can protect all aspects of the QAOA at the cost of an average 13% deviation from the baseline. Today, we discuss 2 software policies. First, we discussed FrozenQubits that improves the reliability of FrozenQubits substantially. Then we discussed Enigma that protects the security of quantum computers. And actually, Enigma is the first SQC technique that are readily deployable on existing and near-term quantum computers. This work highlights the huge potentials in providing architectural supports at the application layer. In fact, I believe that leveraging application-specific policies will enable us to achieve quantum supremacy much sooner. And I already have several immediate projects in mind to start. My students will be able to work on and introduce the concept of application-specific quantum error correction. Also, I would like to continue my work on secure quantum computing and develop techniques against active attacks, where the attacker may tamper with the outputs. Currently, there's no measure for protecting quantum machine learning models, and I would like to address it with my students. Moreover, quantum networks are emerging, and we can anticipate to have access to prototype devices soon. And my goal is to demonstrate that we can use these prototype devices to solve much larger problems than smaller devices. Furthermore, I would like to use or leverage multi-qubit gates that soon will be supported natively at the hardware level for boosting the performance of quantum machine learning models. But I should highlight that these application-specific policies are a focus for the next couple of years, and my research agenda goes beyond developing application-specific policies. My goal is to do full stack optimization for different types of quantum computers. At the programming language level, for near-term systems, I would like to work on developing programming tools for single instruction analog quantum computers and continuous variable devices. In long term, I would like to work on realizing a unified programming paradigm that can provide abstractions for end users from the actual hardware or quantum computers that we are using. At the compiler level, I'm currently involved with developing the first complete compiler for neutral atom quantum computers. For near-term systems, I would like to focus on heterogeneous systems as well as distributed quantum computing. For long term, I would like to develop the first compiler that can support logical qubits and logical operation. In both era, I'm also interested in exploring the possibility of securely delegating compilations to the third parties. At the error correction and error mitigation level, I'm involved with multiple projects aiming to enhance the real-time decoding for surface code, which is the gold standard right now in the industry. For near term, I want to focus on developing error mitigation for analog systems as well as continuous variable devices. And for long term, I would like to continue my involvement in providing real-time for different types of error correction codes, and also exploring the possibility of fault tolerance in other computing models, such as adiabatic systems. I'm also involved in quantum machine learning, and my goal is to bring AI, machine learning, and quantum together. Right now, it has two directions, machine learning and AI for quantum and vice versa. Machine learning and AI for quantum, I would like to start with exploring machine learning, namely unsupervised and graphical models for developing error mitigation policies. I'm also interested in exploring the possibility of developing AI-assisted quantum computing models. Regarding quantum for AI, I would like to continue my efforts in tackling classical AI problems, including Boolean satisfiability, constraint satisfaction problems, and inference. Also, I would like to develop quantum machine learning models for both near-term and fault-tolerant systems. Finally, I would like to mention that I'm also involved a little bit with theory and tackling real-world problems. I have deep background in optimization, and I would like to continue my efforts in factoring numbers. And I would like to start tackling problems in drug discovery. I have several contacts in multiple pharmaceutical industry, and I believe that their knowledge and resources can significantly boost our efforts. Research might take years or even decades to become impactful. Teaching and mentoring students is the place that we can see the immediate impact of our work. In spring 2020, I developed a new course in quantum and taught as the instructor. And I have guest lectured a similar course at Georgia Tech for several semesters since 2020. In near term, I would like to start with offering a new course into the quantum computing, specifically designed for computer science students requiring no background in quantum physics and quantum mechanics. I also can offer a new course in optimization or continue offering existing course, which can cover mathematical optimization a little bit, going over intelligent optimization techniques and converging to quantum optimization without learning quantum. And I can also offer a quantum machine learning course, which will be an advanced course. This will be a long-term for students who have background in both quantum and machine learning. Since 2006, I have mentored over 50 students, and currently I'm mentoring Nargis. She's a PhD student at Georgia Tech, and she recently got her first lead author accepted at ASPLUS, and she's going to present it in 2 weeks. I would like to conclude my seminar by highlighting the impact of diversity and inclusion for me. Most of the time when we talk about diversity and inclusion, we talk about people from underrepresented minorities. I'm from a group with no representative. In the entire United States, to my knowledge, there is no faculty in computer science, computer engineering, and electrical engineering who is blind and involved in any research other than disability-related studies. My involvement and activism in diversity and inclusion has been recognized by Google Lime Scholarship, Markov Fellowship, and 3 Rising Leadership Academy Award by US Business Leadership and Network. I have worked with NSF to identify challenges for students with disability, and I will continue my efforts. In long term, my goal is to establish a program to raise the awareness, and I should highlight that I'm not going to limit myself to just be an activist for people with disability. I see myself ally for all other minorities. It could be veterans, people with different gender identities, race, ethnicity, and so on. Thank you so much for listening to my talk, and I'm happy to have your questions. Feel free to speak up. Thank you.
Thank you very much. So this is a question about Enigma, I think Enigma 2.
Okay.
So the question is, you had decoy vertices and edges. How did you choose the weights for those?
Sure, that's a great question. So I mentioned that the numbers needs to be positive, but we didn't limit ourselves to that. And what we did was we took the actual coefficients from the original coefficient. Now we can create a histogram of that. Here, the frequency can be interpreted as the probability of that bucket. And we can create roulette wheel. If we directly use the probability and use the roulette wheel to generate new number if we put the signs aside, just talk about the magnitude, the output problem, the coefficients will follow the same distribution. But if we use the inverse probability for creating the roulette wheel, what we will have is the output problem. In the output problem, the magnitude of the coefficients after adding decoy coefficients will look like a uniform. That can also, thank you for asking the question. I had this slide and I had a hope that someone will ask, and I appreciate that you asked. And this way, we can also hide the distribution of magnitude of the coefficients.
Thanks. I was hoping I didn't miss that slide.
I'm sorry?
No, I'm glad I didn't miss that slide.
Any other question? And if there's any question in chat, I wouldn't see that. I appreciate someone monitoring the chats as well.
What are the input and output representations that a quantum compiler works with?
Would you please say it louder?
What are the input and output representations that a quantum compiler works with?
Okay, so the question is that, so the input is a quantum circuit, output is also a quantum circuit. The changes that compilers apply is that the operations that we said, for example, Hadamard gate. In reality, the hardware does not support that gate. We have a limited set of operations that are supported natively. So first job is to decompose all those high-level gates to gates that the hardware supports. And these gates can differ. For example, the Google, IBM, and Rigetti, they all develop superconducting quantum computers, but their native gate sets are different. So one of the jobs is the decomposition of those high-level gates into gates that are supported at the hardware level. The second is the routing. As I discussed in FrozenQubits, if we want to apply a 2-qubit gate between 2 qubits, we must first make them physically adjacent. And quantum bits are sparsely connected. So if we want to apply a 2-qubit gate between 2 qubits, one is here, one is on the other side of the circuit, we must apply successive swaps to interchange and route them, make them first physically adjacent. And one of the important jobs in compilers, quantum compilers, is to efficiently doing these routing, because every swap is represented with 3 CNOTs, which is very costly in terms of adding noise and also increasing depth of the circuit. These are 2 main tasks involved in quantum compiling.
Can you say a few words about what kind of resources your students would need in order to work on these kinds of problems? Do they need access to quantum computers, or can they do that work more in theory and then interface
Sure.
later?
Definitely, everyone can start with simulations that can be installed on laptops. For up to 10, 15, 20 qubits, it's reasonable to run simulation on laptop. Up to 30 qubits, we can do it on high-performance computing. But nowadays, all research, we need to access real quantum computers, which is a common standard, and almost all papers have results running on real quantum hardware.
So they use like a quantum cloud
Yes,
service provider.
exactly. I mean, we cannot expect. There are very few cases that universities have on-site quantum hardware, and I believe that in most cases, almost everyone access via cloud.
Okay, let's thank our speaker again.
Thank you.